Okay, this webcast continues making some energy pie charts, and so I'm going to look at here problem 6, where we've got a wind-up toy that's wound up and moving across level ground. Notice that it says the toy is speeding up. Okay, so I'm going to choose 3 places to do my pie charts, and so I'm going to draw 3 circles to represent the energy pies at those locations. Now in the first position, these arrows, these are velocity vectors, and so I can see, because the arrows are getting longer and longer, that the bunny is speeding up. When I first look at him, he's just moving a little bit, and so I'm going to put some kinetic energy, just a small amount. Remember, I do not show dissipation in the first view, and he's wound up, so the rest of this toy's energy is stored in the spring, which has a reversible deformation. Okay, the spring is wound up. Now in the second view, the bunny is much faster, so I should see kinetic energy be larger. The elastic potential energy should be smaller, because the spring is gradually unwinding. But the other thing that's happening here is that the bunny's feet are rubbing across the ground, and so there is some energy that is being dissipated due to friction. Okay, but you and I might choose to draw these in slightly different ways, but the important thing is I should see the piece of pie that is for kinetic energy should be getting larger, because the bunny is moving faster. Okay, I should see some dissipation starting to be shown, because as the bunny overcomes friction, some of his energy is going into the E-dis storage mode, and I should see the elastic potential energy getting smaller, because I know that the spring is gradually going back to its original position. Now at the end, the bunny is moving even faster, and so I want to show even more kinetic energy. The bunny has moved a longer distance, and so I'm going to show E-dis being bigger, and I'm still going to show a little bit of elastic potential energy. Once the spring is totally unwound, the rabbit will stop moving, but the rabbit is still moving, so I think there is still a little elastic potential energy here. But again, the important thing is the relative changes in the pieces of pie. So I'm showing kinetic energy getting bigger in each successive pie. I didn't show any dissipated energy at the beginning, because you never show it in the first view, but I show it getting bigger from the second pie to the third pie, because as the bunny travels further, more friction has to be overcome, and so more energy is dissipated. And I'm showing the elastic potential energy getting smaller and smaller. Let's do another one of these. This time we've got, the same kind of toy, but now the bunny is moving at a constant speed up an incline. Okay, so constant speed, but the important thing here is it's moving up. Okay, so again, I chose 3 positions in this path, and so I'm going to do 3 pies. I'm trying to draw them all the same size, we can't draw them perfectly. Okay, at the beginning, the toy is moving, right? Because I see the velocity vector, and it is fully wound up. It's on the ground here. On this one, it's on the ground. So I'm going to just choose a size of the piece of the pie to be kinetic, and then the rest of this is elastic potential energy. At position B, it's still moving at the same speed, so the kinetic energy is the same. But now there is height, right? It is higher than it was originally, and so now there is some gravitational potential energy. Its little feet have been rubbing against, against the floor, so there's some dissipated energy, and the elastic potential energy is getting smaller. Okay, and now I'm going to go up and show position C. Again, the speed is the same, and so the kinetic energy is the same, but look, now it's at a much higher height. Okay, so the gravitational energy is bigger. It has traveled further, and so it has overcome more friction. The dissipated energy is bigger, and this little piece right here is the elastic potential energy. I'm still showing some elastic potential energy because the rabbit has not stopped moving yet. Let's look at another one. Okay, in this one, it's similar, but now it is slowing down as it moves up the incline. So let's see how we might show this scenario. So again, I'm choosing 3 positions to show the energy pie charts. At the beginning, it's moving pretty fast, and it is wound up, and so the rest of its energy is elastic potential energy. Right here, it's on the ground, right? Okay. At position B, it has moved up to a taller height, and it has slowed down. So I'm going to make the kinetic energy smaller. I'm going to show some gravitational potential energy. I'm going to show a little bit of dissipated energy because the feet have been sliding against the ground, and elastic potential energy is getting smaller. At the end, here at position C, it's moving very slowly. So I've just got a sliver, maybe, of kinetic energy, but the gravitational energy is much higher, right? It's much higher than it was before, so I'm going to show a big amount of gravitational energy. I'm going to show more dissipated energy and a little bit of elastic potential energy left. So, the absolute sizes are not critical, but what I really need to show as I go from A to B to C, the kinetic energy piece of the pie needs to get smaller because it's slowing down. The gravitational potential energy, there is none in A, and then I have some in B, and I need to show a larger amount of EG at position C because it's gotten higher. The same for dissipated energy. There is none at position A when we first start, but I need to show a little bit at position B, and I need to show a larger amount at position C. And the elastic potential energy should be getting smaller at each successive position. Okay, let's go on to a couple that have let's see. Let's look at this one because this has a battery-operated toy car. So a battery has chemical energy. We haven't used any chemical energy yet, but occasionally we need to be able to show energy that's stored as chemical energy. And so this is going to be A, B, and C. So I'm going to show my 3 pies of energy. Okay, now it's moving at a constant speed, and so I'm just going to choose a 1/4 of the pie because I know that the kinetic energy is going to be the same amount in each view. But at the beginning, the rest of the energy in this toy car is in its batteries, right? There is no gravitational energy because it's on the ground. There is no elastic potential energy because there is no reversible deformation. So it's all chemical energy and kinetic energy. Well, after it's moved some distance along the ground and we've gotten to position B, some of the chemical energy has been, used. So we have less chemical energy. What is the rest of this piece of the pie? It needs to have the same energy. Oh, that's dissipation, right? The wheels are rolling, sliding against the ground, and so some of the energy is being dissipated to overcome friction. And then when we go to view C, again, more of the battery chemical energy has been transferred out of being stored as chemical energy and has gone to overcome friction, and so we have an even larger piece of the pie that is that's attributed to the dissipated energy. And then finally, let's look at a bouncy ball. So it's bouncing up and down, and initially it was held at a very high position. Notice it says it's not moving right here. And then it goes down and it strikes the ground. And it doesn't move for just an instant, but it is deformed when it hits the ground. And then it bounces back up, and we're looking at it at C at the top of the first bounce where it's not moving. At the peak of its height, the velocity is 0. Then we look at it at the next peak. Each peak is a little bit lower, and then and so on. So we're going to look at 1, 2, 3, 4, 5, 6 positions. And so I'm just going to go ahead and draw 6 pies here. And I'll label them as they're labeled up above. So at the beginning, the ball is very high. It's being held off the ground. It is not moving. And so in this case, we have something that is starting with gravitational potential energy. When the ball bounces and it strikes the ground the first time, it is deformed. It's a rubber ball. And so the shape changes, but it's a temporary change. This is a reversible deformation. And so, it has some elastic potential energy while it's deformed. But there's also some dissipation that happens. So, and that's the reason that on each successive bounce, it gets a little bit lower and lower. Gradually, more and more of the energy is being dissipated. Okay, so at position B, at the bottom of that bounce, the ball is deformed, and so it is storing some elastic potential energy, and each time it strikes, a little bit more energy gets dissipated. Okay. Now we go to the top of the first bounce. That's position C. Now there's no kinetic energy there, it's just gravitational energy. But remember that fact about dissipated energy. Once you dissipate energy, you cannot get the energy back out. So that same size piece of energy is still dissipated. But now, instead of being stored as elastic potential energy, the energy has moved back into the gravitational potential energy storage mode. So we didn't add to the dissipated energy as the ball moved through the air. We're ignoring any air resistance or anything for this little ball. But the energy that was dissipated on that first bounce, that energy remains dissipated. We can't move that out of that piece of pie. Okay, now D is looking at the ball at the top of the second bounce. So even though, as the ball hit the ground the second time, more energy was dissipated. And so D is different than C in that the piece of pie that is dissipated energy has grown. It's, let's say it's doubled in size. Okay, now at position E, the ball is starting to fall down after the second bounce. It's speeding up, right? So at C and D, there was no kinetic energy because at the peak of the bounces, the ball does not move just for a second, just for a fraction of a second. Okay, so I have the same amount of dissipated energy. I haven't added anything to it. But now the ball is falling, and so it has less gravitational energy, and since it is moving, it has kinetic energy. And then finally, we get all the way over many bounces later, the ball finally comes to a stop on the ground, and it's not moving. At this point, all of its energy has been moved into the dissipated category.